This is a very interesting question asked by one of our students, which is why are we even using regularization in linear regression? Because we have introduced regularization, especially L2 regularization, in the case of logistic regression by saying that if the values of W tend to infinity, then the whole problem, the whole optimization system will go crazy. The question here is, the question here is, such a problem doesn't seem to occur here, right? Such a problem doesn't simply seem to occur. So why do we need even this term? So this is the optimization problem that we solve as part of linear regression, right? We're trying to find a W or a W star which minimizes my squared error. This is my squared error, right? This is my squared error. Squared error plus some lambda times, here lambda is the hyperparameter, some lambda times my L2 regularizer, right? This is my L2 regularizer. Now the fundamental question is, why do we need it? What happens if it's not there? So we thought it's good to give you an example. We'll try to work out the need for the L2 regularizer. We can have even L1 regularizer here. Now let's try to construct using a small simulated example so that you understand this concept better. But this is a very, very good, very, very valid question. Okay, so let's go step by step here, right? So let's assume I have three features, right? And my yi is equal to W transpose xi, right? This is what your linear regression relationship between xi's and yi's, right? You have a linear model, right, where your weights are multiplied by the data that you're given to obtain your yi, right? Now let's assume I have three features. Let's assume I have three features, which means my xi belongs to R3. Similarly, my W belongs to R3 and my yi, because it's a regression problem, belongs to real values. So if I have to rewrite this, I can write it as yi equals to W1 xi1 plus W2 xi2 plus W3 xi3, right? This is the relationship, right? So let's look at a real world example. So we'll look at a simulated example and a real world example, right? So imagine, so let's look at the simulation first and then we'll go into the real world example. So imagine, to understand the need for regularization, let's assume I construct data. Okay, I construct my data as follows, right? I generate data such that yi is equal to 2 times xi1 plus 3 times xi2 plus 0 times xi3. Okay, suppose, imagine if I just create a table. Imagine if I just create a table like this, right? This is my feature 1, feature 2, feature 3 and my y values, right? Now here I'll generate random values for xi1, xi2 and xi3. Okay, so this value, so let's assume this is xi, right? This is xi1, xi2, xi3. I generate all three of them randomly, and when I plug these values, let's assume I generated value of 1 here, value of 2 here, value of 1.5 here. When I plug these values at these places, I'll get my value of yi. I'll put that value of yi here, right? So 2 times 1 is 2, plus 3 times 2 is 6. So I'll put the value of 6 here, because 0 times 1.5 is 0. So I can construct a data set like this. So let's call this my simulated data set. My simulated data set. So this is artificially constructed data set that I'm constructing here. Then what I would do here is I'll take this artificially constructed data set. Let's assume I created some 10k such points. So here, this is very important. I'm just randomly picking up values for feature 1, feature 2, feature 3 for any point xi, and I'm computing the value of yi through this function, right? So this is the underlying. So this is the underlying function or the relationship between your yi and xi. Suppose now, if I take this, suppose somebody generated this. Suppose I generated this for you. And actually I gave you the simulated data set. Let's call this data set D. Okay. Suppose I've generated this and I gave you D and asked the question to you, which is, now can you fit a function? Can you fit a linear function? Or in other words, can you find the vector W? That's what we're trying to do, right? In linear regression, effectively, we're trying to find the optimal W. So imagine if somebody created this data set for you, simulated this data set, they didn't tell you these weights. They withheld these weights with them. They just gave you the data set. right? And they asked you to fit a linear regression model. They asked you to fit a linear regression model. And at the end of it, what is the ideal solution here? The ideal solution here is that your W vector is 2, 3, 0. Because this data to start with was simulated using this underlying relationship, isn't it? So this should become your W1, this should become your W2, this should become your W3, right? Clear till now, I hope. So we are simulating a data using an underlying function. And if somebody gives you this data and asks you to build a linear regression model, what is the ideal solution? The ideal solution using this 10,000 points would be exactly determining the weights that were withheld from us. Okay, all well? This is like a simulation. In the real world, what happens? So let's see what happens in the real world. Imagine my y is my heights of people, right? And my feature 1, let's say, is their weight. Let's assume my feature 2 is their age. Let's assume feature 3 is their gender. Right? Imagine my gender represented as 0 or 1 or 1 and -1, whatever you want. Age is a real valued number, weight is a real valued number. So if somehow you want to predict height of a person given their weight, age and gender, and if you know that there is some linear relationship between them, what actually happens in the real world is when you're measuring your weight, okay, let's assume the optimal weight, the actual weight of a person. So let's take one person xi for whom you're computing their weight, age and gender. Let's assume the weight of xi, this person, is let's say 60.262 kilos. But we don't actually encode that in our table when we write it in our table, right? When we write it in our table, this is my weight, age, gender and height. We don't exactly encode it as is. We'll have a small error. We could say this person's weight is 60 kilos. Similarly, let's take age. The person's age may be, let's say, 30.23 years. But we might just encode that because these all are errors that we introduce into the data, right? We could just say his age is 30 years or 30 and a half years. Gender, there is no error. We'll just say either male or female. Even in height, there will be errors. Let's assume a person is 162.262 centimeters. We could just write it as 162 centimeters. Right? This often happens. So what is happening in the real world is we are not encoding the original data as is. We're introducing a small error because of rounding or whatever. Here the error is occurring because of rounding. Right? Similarly, in the simulated data also, sorry. In the simulated data also, you have your yi, which is 2 times xi1 plus 3 times xi2 plus 0 times xi3, right? In a non-real world, we would just generate data by plugging in some random values of feature 1, feature 2, feature 3 and obtaining yi. But if you really want to simulate, if you want to simulate the real world closely, you know that there will be small error associated with each of these. So you can add a small error term here. A small error. See, epsilon I is a small error that you are adding, right? So because by then, even though your underlying function, remember your underlying function, this is very important. Your underlying function is yi equals to 2 times xi1 plus 3 times xi2 plus 0 times xi3. This is the underlying function. But when we are simulating the real world data, because in the real world, there will be all these small errors that are actually introduced in the real world, right? You want your linear regression formulation to work in the real world, not just on simulated data, right? So to simulate real world like data, we are adding a small error term. And now you create your data set. Let's call this data set D dash. D dash is a simulated real world data with the underlying function. Again, remember, this is the underlying function. But this in the simulated data, we'll add a small error term, right? So that whatever data we are simulating, let's assume I create 10,000 data points here, right? This is simulated data because in the real world, data is never perfect. There will be all sorts of abnormalities, outliers, noise, tons of things. Now on my new data set D dash, remember this data D dash is different from D. D is perfectly simulated data. D dash is a real world simulation using errors. Now comes the fun part. Now let's assume I'm given D dash. I'm not told of this underlying function. Suppose you generated this, you didn't tell me the underlying weights. You didn't tell me that W1 is 2, W2 is 3, W3 is 0. But we simulated this data using errors, right? Now comes the fun part. Suppose you gave me this 10,000 data set, this data set of 10,000 points, which is a real world simulation, which is a real world simulated data, which is a real world simulated data with this underlying weights. Now comes the fun part. Now imagine two cases. Case one, I apply linear regression. I apply linear regression without, okay, plus no regularization. Suppose I don't apply regularization. What happens to your weights? Okay, because this data is slightly corrupted by noise. Remember, this data is this noise is small. Remember, this is small error or small noise. Because my data is slightly corrupted by my noise, how will my optimization function look like now? This term won't exist. I'll only have a squared loss minimization. Okay, I will only have this part. Right? Here, what is it worried about? It is worried about. So I passed my D dash into this optimization problem. Now what it will try to do? It will try to minimize the squared loss as much as possible. Right? On the training data. Again, this N here is the set of all the training examples or training points. Now, when you have no regularization, right, the final weights that you get, would not be exactly 230. Because there is a small noise, what will happen? Because look at your optimization problem. Your optimization problem is just about minimizing squares. You don't have regularizer yet. So there is no incentive for the optimization problem to think of W's. It will try to fit your W's as closely as possible to the training data. So the final weights that you get would typically look like 2.1, 3.06 and 0.12. Your weights, remember, what is your underlying weights? W underlying. What are our underlying weights using which we generated the data? 230. The underlying weights are 230. When we used no regularization, when we did not use any regularization, we get values which are slightly away from this. And why did we get these values away from this? Because there is noise introduced in the data. Now, when there is noise introduced in the data and when there is no regularizer, all it's trying to do is to minimize the squared error. It is trying to minimize this gap between yi and w transpose xi. That's what it's trying to minimize. And in doing so, it will obtain weights which are not same as the underlying weights. Now let's take case 2. Okay, let's assume I have linear regression plus some regularization. Right? Now this regularization, when we apply regularization here, we would mostly get values like this. We would get values. We will not again get perfect 230, but we would get values which are closer to the original values than without regularization. Now your question is why? The reason being, when there is a small noise introduced, right? Without regularization, we got what are the values trying to achieve? They are trying to simply, when you have no regularization, they're trying to simply minimize the squared loss. But when I have regularizer, I have this additional term. This whole problem becomes, and what is this regularizer trying to do? The regularizer is forcing the WIs to be small. The regularizer is forcing your WIs to be small. Of course, here lambda will control how much is the balance between your error and your regularizer. But we'll determine the optimal lambda using cross-validation. But overall, because we have these two terms, so now what is optimizer trying to do? Optimizer is trying to reduce the error, and while doing so, it is also trying to ensure that the values of Wi are small, right? So the moment we introduce your L2 regularizer, right, it will try to pull these values down as possible, right? It will try to pull these values down such that, of course, you can't just make them zeros. Let's assume it made them zeros, right? Then your loss will increase, right? It's like a balance. If it just made these all weights zero, this will shoot up, right? So if you look at the whole optimization scenario itself, you have loss, you have your squared loss plus some lambda times your L2 regularizer. The L2 regularizer is trying to reduce your WIs. This is trying to reduce your error. This is trying to reduce your error. So there is a tug of war that's happening between these two things, right? In this tug of war, what happens is when you introduce regularization, these values will not be, since they're not just minimizing squared loss, they're also being forced to be as small as possible, right? You tend to get values which are closer to the underlying weights in the simulation, right? I hope this becomes clearer now. So regularization is a way to control our weights from not overfitting. Again, remember, in this case, what happened? Because we don't have regularizer, because we don't have any control on WIs. In this case, we don't have any control on WIs. So WI is no control. When there is no control on WIs, they'll try to overfit to the data, even to corrupted and noisy data. Remember, your D dash was generated using some error and noise. But they don't care. They are just given a data set. When you don't have any regularization, your weights are not controlled in any other way except through loss, right? So they will only try to minimize the training loss, which means they will overfit. In the other case, when we introduce regularization, we have an additional control. We have this additional control over regularization, which is controlled by lambda. And this ensures your WIs don't become unnecessarily large. And this happens a lot. You can run this simulation yourself. You'll notice this a lot. Of course, you have to find the optimal lambda using cross-validation. Okay? And these types of weights, which are closer to the underlying weights, tend to generalize well on new unseen test data. Remember, what we want at the end of the day, the whole objective of regression is to take some training data, find these weights which will work in the future on unseen data, right? So this is the argument behind why we have regularization in the first place in linear regression. I hope the question is clear now.